Okay, section 4.6. We're still going to do a little bit of proofs on this, okay, but we're not doing the side angle, and all that kind of thing on this anymore. We are going to talk about isosceles and equilateral triangles, and I just happen to have an isosceles triangle, okay? And I did make this so that it is isosceles, these two sides right here. Now remember what isosceles means, though. And let's spell it right. Look, this is how we spell isosceles. Isos, right? And then Celes, C-E-L, like Celine Dion, right? C-E-L-E-S.
I don't even know how to spell Celine.
You don't know how to spell Celine Dion? C-E-L-I-N-E, Celine. Anyway, so that's isosceles. So what does isosceles mean? Does it mean that it has exactly two sides equal? At least two of the sides equal, two or more, okay? So, but for the most part, we're going to kind of use the word isosceles when exactly two of the sides are equal. But technically, if all three sides are equal, I could technically call that an isosceles triangle, couldn't I? Yes. All right. Yeah, you could call a square a rectangle, but can you call every single rectangle a square, though? No. Can you call every isosceles triangle equilateral? No. Can you call every equilateral triangle isosceles? Yes, you can. Okay, you got it. So isosceles triangle, two sides are equal. Let's just give these a name. The two sides that are equal we call the legs of the isosceles triangle, and the unequal, if there is an unequal side, we would call that the base. All right, so if this side right here is not equal to the other two sides, we'd call that the base. All right, and then they would all be legs. Yeah, if it was equilateral, they're all three legs. All right, and okay, we'll call this angle 1 right here. This angle right here, they call this the vertex angle. The vertex angle. How do I know this is the vertex angle, not this one or this one? What do you think, Miriam?
Because that's... Oh, I was going to say it splits it into two, but I guess they all split into where the two legs meet.
It's where the two legs meet. Okay, you could say it that way. Or it's opposite what? The base, right. Okay. Call that the vertex angle. It's opposite the base. We call these, and look at this right here. This angle right here does not touch the base, does it? All right. But this angle does. So if I call this 2 and 3... See these two angles down here? They do touch the base. So guess what angles I'll call those? Call those the base angles. Okay, so that would be a base angle. So you have two base angles, don't you? And that would be a base angle right there. And how do you know it's the base angle? Because the angle is formed by one of the bases, by the base. Agree? Okay, good enough. That's enough vocabulary on there. Let's do a theorem. This is an actual theorem. So the next thing we're going to talk about is a theorem with this. And they call this, it makes sense, the Isosceles Triangle Theorem. All right. You'll have a couple theorems. Yeah. And we'll have another thing called a corollary. You ever hear of a corollary? Well, you will in a few minutes. All right, so this is called the Isosceles Triangle Theorem. And what it says is this. If you have an isosceles, which means you have at least two sides equal to each other, agreed? All right, so if you have an isosceles triangle, the angles, the base angles, let's see how they say it. Yeah, they don't even refer to it as the base angles. They say the angles opposite the two equal sides. Yes. Yes. The angles opposite the two equal sides right here. Let's think about this. What do you think might be true about this? If this side right here and this side right here were equal to each other, what do you think might be true about this angle and this angle right here? Yeah, they're going to equal. Because, watch, if these two sides were not equal, let's see if I can do this. Let's ungroup this so I can split them up. Watch this. If I take this side right here, and I'll hit R for rotate, click on that, so it should rotate around here. Watch this. If I slid that around, see what happens? In order to make a triangle, now it looks like it keeps touching all the way through, but as soon as I start moving it this way, it looks like it's touching, but really what's happening, it's not touching. It only touches right here, right? If I move it that way, it's off of there, right? If I move it just a little bit this way, even though it kind of looks like through this whole process right in here, it looks like it's touching, doesn't it? Technically, it's really not. All right. So as soon as I start going like this, it gets shorter. So if I change this side, watch this. If I would have to change the length of it, wouldn't I? So by changing the length of it, what did it do to that angle? It changed the angle, didn't it? But if it was like that, and this side were exactly the same, these two angles are going to be what? Exactly the same, okay? It's not really a proof. I'd have to figure out how to prove this. I'm not really sure how to prove this, but anyway, here's what this theorem says. That these two sides, if they're equal to each other, then the base angles are going to be equal to each other as well. Or the angles opposite the two equal sides will be equal. That's what the Isosceles Triangle theorem says. Basically, if two sides of a triangle are equal, then the opposite angles will be equal as well. I really shortened it quite a bit there, didn't I? But it basically says what we want it to say. If two sides of a triangle are congruent to each other, which makes it an isosceles triangle, doesn't it? So if two sides of a triangle are congruent to each other, or equal to each other, then the angles that are opposite those two equal sides, right? Then the opposite angles, you know what I'm saying? The opposite angles of these two equal legs would be equal to each other as well. So if these two are equal, then what? These two are equal. So if the two sides are equal, then the two opposite angles are equal. Make sense? It's a little wordy, you know, the way they write it. I'm just trying to shorten it so makes a little sense. If the two legs are equal, then the two base angles are equal, if you want to say it like that. Got it? What do you think might be true the other way around?
If those two angles are equal, then
You got it. Exactly. And that's the converse. Remember we talked about converse before, earlier in the year? Remember the if-then statement? We talked about this, didn't we? We use P and Q to represent if and then. The P represents the if part. Did we talk about this?
No.
We never said this before?
No.
Oh, wow. I thought we did. Anyway, in logic, I guess, when we do these if-then statements, they use P to represent the if part of the statement. So this says if what? If the two sides are equal. Agreed? And then the arrow represents the then. So if P is true, then Q is true. You follow me? So what is this? What's the P part of this statement? Two sides of the triangle are equal, right? So do we have two sides of the triangle equal? Yes. So if P is true, then what? Then Q is true. What is the Q? The opposite angles are going to be equal to each other as well. Well, what if you switched it around? What if you went if Q, then P? This right here, if we switch around the if and the then, this is called the converse of the statement. All right? Yeah, write it down. So this is the actual statement itself. P, if P, then Q. The converse would be if I switch it around. Now, the converse is not always necessarily true. Okay? If the statement's true, the converse isn't always going to be true. In this case, though, it is. If both of these things are true, watch this. If P, then Q, if that's true, and then if Q, then P, if that's true as well, if both of these things are true, this is the way we would write it. We'd say P, if and only if, Q. And sometimes they'll write it like this. You'll see IFF for if and only if. It's just a shorthand, shortcut. If and only if. What does this mean? This means if P, then Q. That statement is true. I could go the other way. That's why there's arrows going both ways. If what? Instead of if P, then Q, then also if Q, then P. So those two arrows mean these two things right here instead of writing it as two separate things. We just write it as one little thing. All right? It means P is true if and only if Q is true. You got it? So what this is one of those deals. So the isosceles triangle theorem says this. If the two sides are equal, then the opposite angles are equal. All right? So the converse, I'll just put CONV, of the isosceles triangle theorem says, what do you think? If what? If the two angles, you could say opposite, if two angles of a triangle are congruent to each other, then, what do you think? Then the opposite sides are equal. Good. Excuse my writing, a little sloppy today. Opposite, oops, why did I put opposite twice? The opposite sides are equal. See what we did here? The theorem itself says if you have two sides of a triangle that are equal, then those two opposite angles are going to be equal as well. Or you can flip it around. Do the converse of it. The converse says this. If you have two angles of a triangle equal to each other, and that's all you know, two angles of one triangle are equal to each other. What does that mean then? it means the opposite sides are going to be equal to each other as well. Does that make sense? So let's I ungroup these, so I'm going to have to select them again, group them again, and let's slide this down. So basically it says this. What if I knew, let's call this ABC. Let's say I knew that angle B and angle C were equal to each other. So watch. If angle B equals angle C, then, let's use letters here. What can you conclude from this? If angle B is equal to angle C, if they told me, if it was given, all right, if there was a way I could figure it out, if I knew that angle B and angle C were equal to each other, then what can I conclude from that theorem that we just talked about? What do you think? Then AB, the length of AB, is equal to what? The length of AC. You follow me? So, no, it's not really, because the third angle theorem says if two angles of a triangle, well, let's see. If two angles of one triangle equal two angles of another triangle. See, I'm not even introducing a second triangle on this theorem, am I? So the third angle theorem says if two angles of one triangle equals two angles of another triangle, then what? The third angles are equal to each other. This is really quite a bit different. So this says if two angles of one triangle are equal to each other, then what must be true? Then the opposite sides are going to be equal to each other. Got that? Now, what is that? What if I said why? What's my reasoning? If this was a proof, and I gave you that B and C were equal to each other, and you said that, okay, if B and C are equal, that means AB and AC are equal to each other. Why? Give me a reason. It's the converse, right? It's the converse of the isosceles, I'll just shorten that, triangle theorem. Okay? Make sense? That's the converse. What's the actual theorem say, though? The actual... Yeah, so let's do the same thing. Let's call it ABC again. All right? So what's the actual theorem say? It says this. If what? AB is equal to AC, then what must be true? If AB equals AC, then what can we conclude? Right, angle B equals angle C. Good. Why? What's the reason? That's it. It's because of the isosceles triangle theorem. Okay? Make sense? So if the two sides are equal, that means the two angles are equal. Why? Because the isosceles triangle theorem. What if they give you the B and C, the two angles equal? Then you can conclude that AB is equal to AC. Why? Because of the converse of the isosceles triangle theorem. Get it? All right, easy enough. We did that. Let's... Okay. This is something we talked about. I'll tell you what, let me... All right, here's a triangle right here. Now, it just happens that it's an equilateral. But I could also call it a what? Isosceles, right. Okay. But most of the time, if there's three sides, we'll call it equilateral. If there's only two that are equal, we usually just call it an isosceles. But technically, you could call this an isosceles as well. So I've got two angles right here. Now, what I'm going to do is that we're going to actually do a little proof, kind of a little proof. We're going to come up with our own little theorem here for a equilateral triangle. So if I said that this angle and this angle, let's call it A, B, and C, so we can refer to these things. And make my point size bigger. Okay, so here's triangle ABC. What if I knew that AB was equal to AC, which I do know because I've marked them right here? What do you think we can conclude about some of our angles? That angle B is equal to angle C. That's old news, isn't it? We just talked about that. But guess what else? Look at this. AC and BC are also equal to each other, aren't they? So what must be true about those opposite angles of those two? So A and B must equal each other, right? And again, what's the reason? Because of the what? Because isosceles triangle theorem, right? Guess what we just did? We just proved, that's right, we actually just proved that all three angles of an equilateral triangle are also equal to each other, okay? What's that? Well, you don't know that all the angles are equal. We haven't proven it yet. Yeah, but we don't have a theorem. We never had a theorem that said that, though. We can only go by the stuff that we know previous, okay? So what did we know already? We knew that if two sides were equal, then the two angles, the opposite angles are equal, right? That's the only thing we knew. Now, we did discuss this a while back, but we never did prove it. We never had a theorem that said this was true, all right? So we couldn't just look at it and say, oh yeah, Mr. Hammer, you told us if all the sides are equal, then all the angles are equal. And I might have, all right? But we kind of got ahead of ourselves a little bit. But at this point, we can only go by the information they give us, right? And what do we know so far? We know the triangle, the isosceles triangle theorem. We know the converse of it. So by knowing that these two sides are equal, that tells us B and C are equal. Why? Give me a reason. Isosceles triangle theorem, right? You could also say that, okay, if AC and BC are equal to each other, that means angle B equals angle A. Again, because of the same reason, right? Because of the isosceles triangle theorem. So if angle B has one arc, guess what angle A has? That's got one arc as well because they're equal to each other. Agree? Or you could have done this. You could have said, okay, AB and BC are equal to each other. That means A and C are equal to each other. Got it? If this has one arc, that has to have one arc. Make sense? So we basically just proved that if all three sides of one triangle are equal, guess what's true about the three angles? They're going to be equal as well. So that means if we start off with an equilateral triangle, okay, that means an equilateral triangle is always going to be what? Equiangular. Okay. It is. Well, it's actually, we kind of got this from that isosceles triangle theorem, didn't we? It's kind of like a spin-off. You heard me say that before? It's kind of like a spin-off of that theorem. Anytime you have a spin-off of a theorem, they call it a corollary. Make sure I spell it right. Yeah, it's an O. I was just making sure. All right, a couple O's in there. So this is a corollary. It's basically just like a theorem. You can prove it just like you can prove a theorem, but it's kind of, it's like a sub-theorem, if you want to call it that, right? You got this big main theorem right here, and then underneath of it, we kind of used that theorem to come up with this whole thing, didn't we? Does that make sense? So it's kind of like a mini theorem, if you want to use that terminology, I guess. But they call this a corollary because it definitely has something to do with that isosceles triangle theorem. So you got this big old isosceles triangle theorem. Underneath of that, we use that theorem to come up with this theorem. But they call it a corollary just because it has something to do with that first theorem. Now, if it's equilateral, that means it's equiangular. But you could also do what? You could also say, watch this. What about this? Let's say this was given. Well, it's given that it's equiangular, right? So if this angle equals this angle right here, well, it must be true. The opposite sides must be equal. Agreed? Why? Because the converse, right? It's because of the converse of the isosceles triangle theorem. So let's do this. What about these two sides, A and B? Or these two angles, sorry. If A and B are equal to each other, guess what must be true? Then the opposite sides are equal as well. Agreed? So that's got to be true. So if they're equilateral, then they're what? Equiangular. If it's equiangular, guess what? Then it's equilateral. So I could say this. It's an equilateral triangle. Well, you could just go both ways. That's an if and only if statement. Let me give you a couple problems to do, because we pretty much did enough. I was hoping we have some time to do an example or two, but you can look in the book. There's a couple examples in there, but I think you can handle it. So here are the problems. It's section 4.6, pages 287, 288. Numbers.
Buddy Smith, Baron Carlson,
9 to 22.
Brandon Yeager,
That's
Miranda
it.
Bollinger, please come to the office.
No, I don't think any of them are proofs. I got some proofs for you to do tomorrow, though. I don't think any of these are proofs. You'll figure it out. Because if two angles are equal, then the opposite sides are equal. If two opposite sides are equal, then the angles are equal. That's going to help you out. I promise you. I think you'll find this fairly easy. I really do.